Yeah, actually, out of curiosity, how many people are interested in trying to do the Monte exam? Just some of my friends. All right.
I don't think I can make it, but
I can. Yeah, if you decide that you would like to do it, I can organize a couple days after school, a couple days before school. It won't give you the full picture, but you can at least kind of get a score going. All right. So what we did last class is we barely started the 9.4 notes. But we talked about a relationship to geometric series. So we kind of created this guy as our last guy to build off of, where we had our geometric series with a equals 1 and r equals x turned into that rational function using our sum formula for geometric series. So we're going to talk a little bit about how we can use this to build a new series, and then talk slightly about interval of convergence before we kind of finish up. So looking at this, I want to scroll down to kind of this question right here, where we're going to find a power series for f of x equals 1 over 1 minus x squared. Now I want you to look at this series here and this series here and tell me how I got from that one to that one using some of the things that we've done to power series so far. So how could I change this into this? All right, I could essentially plug in x squared where x is. So my r is now going to be x squared, yes? All right, so let's write down f of x. So, hello, x squared. What would our a be for our geometric series? Our first term, 1. So what is our first term? 1. What would the next term be if r is x squared? X squared from 1 times x squared. What would the next term be? X to the 4th. Let's get people unlost. How are we getting from one term to the next term? We're multiplying by the common ratio. All right. What would the next term be? X to the 6th. All right. One thing you can also do is if you're building off of these terms, this is the same as the 1. I plug in x squared where x is. I plug in x squared where x is. So x squared squared is x to the 4th. The x squared cube is x to the 6th.
Just for one of them, write out what you're actually like the whole like.
What?
Is it literally just like?
Yeah. So you could plug it into the one we have, or literally we're just taking this and we're multiplying by x squared. All right. So how could I write this formula? How could I write this general term? What could I write? X to what power? So I could write squared plugged in to x to the n. How could I simplify this though? X to the 2n. And that makes sense because I'm getting a bunch of even powers. Now, we actually get a kind of cool conclusion about interval of convergence here. So this is asking for what values of x does my series converge. That reminds me of doing interval of convergence. Does anyone remember how we did interval of convergence in the like 9.2 notes? We tested endpoints after we did ratio tests. That's a whole big thing that we can actually avoid because of what type of series this is. How did we build this type of series? What type were we working with where we multiplied by the common ratio? Geometric. When does a geometric series converge? When r is less than 1, or the absolute value of r is less than 1. Do I already know about, let me write and not talk at the same time. Do I already know what happens when r equals 1 for geometric series? What happens if r equals 1? We diverge, right? Not harmonic. That would be like p series where p equals 1. R equals 1 would be like I have maybe my first term is 1 and then I multiply by 1 every time. so I'm adding up infinitely many ones or infinitely many of whatever the first term is, that's going to diverge every single time.
You have a lot of absolute values on the plus side.
That is fair. So the cool part about knowing this is built off of geometric is we don't have to do what Nicole brought up. We don't have to test our endpoints because we already know they diverge. So we want this to be less than 1. X squared is always positive. So I want X to be between what two numbers? If X squared is less than 1. Perfect. All right, so this would be our interval of convergence. And because we got our knowledge from a geometric, we don't have to test our endpoints. Now we would just get both of them diverge. But because we're making it off of geometric, we can kind of get around that. So we're going to try to practice the thing we started last time. I'm going to do a few of them just to get you guys in the kind of mood that we were in. With those 3 sets of directions that we had before. So remember these 3 sets: change the center, make the 1, make the minus. We're going to make this make a little bit more sense. Speaking of interval of convergence, though, we actually didn't do that with this series. Let's just do it real quick. For what values of X does our series converge? We made this one based off of geometric, right? What was our R for this one? Negative X over 4. And for this to converge, what would we want our R to be? Less than 1 when we absolute value. So if I'm kind of solving this, I could have my absolute value of X, I'm going to multiply by 4 on both sides, is less than 4. What? I did not ask you to do that. Y'all, my new computer is the worst. What did you say? I don't think we can blame Putin for this one. All right. If the absolute value of X is less than 4, what 2 numbers should X be between? 0, -4 and +4. All right. Do I have to check the endpoints? No, because I made it off of a geometric series. So it's kind of a workaround for interval of convergence if you have a nice series like this. All right, so what I want to focus on now is the process we did right here in the actual writing. So what we're going to do is we're going to take a rational function and we're going to try to make it look like the sum of a geometric series. So a number over 1 minus our stuff with our center going. So what we did last time, we didn't have to change the center because this one was centered at 0. So I could just isolate the X by itself. And then we focused on this part of our sum right here. We made the 4 a 1 by multiplying by 1/4. And then we broke the plus into minus and negative. So I had that minus from the A over 1 minus R. What we didn't do in this one is change the center. So I want to show you how to do that first. And then we're going to practice a bunch. This is a great one for a multiple choice question on Taylor series. So you're probably going to see this on the AP test. So let's start with, how do I fix the center? Can you guys read this question and tell me what the center is? Cool. Nice reading. All right. Usually when we see the center, we see X minus the center in our kind of formula, right? So I should theoretically see X minus 3, right? I cannot subtract 3 wherever I want, or just like put a minus 3 in there. So I have to compensate for the fact that I put this here. Now, did I technically subtract 3 from the bottom of this guy? No, technically, because of that minus a -3, that was me adding 3. So what should I put right here so that this denominator is equivalent to this denominator? -3. So if I resimplified back out, that whole denominator would equal the original one, right? All right, let's simplify a little bit. I'm going to keep the 5 at the top, and I'm going to combine like terms on the bottom, really trying to preserve that X minus 3. I need to see X minus the center. So what is 4 minus 3? Ooh, terrific. Is anyone else excited like I am? Let's look at our steps again. Never. It's the answer to that question, just never excited. All right. So I changed the center. I can see my x minus 3. Make the 1. Is the 1 where we need it to be in a over 1 minus r? Yes. Make the minus. Is the minus where I need it to be in a over 1 minus r? Yes. So how fortunate for us. So what is a? 5. What is r? X minus 3. So we're going to write the first 4 non-zero terms and then general term for this series. Are you ready? What's the first term? 5. What's the next term? Remember, we said that we multiply by the ratio, so 5 times x minus 3. What's the next? No, we're good. Remember, for most of these, we want to see x minus the center in every single one of our terms. It's kind of the creepy way we write them. All right, Lily's claiming 5 times x minus 3 squared. Did she multiply by x minus 3 correctly, preserving our x minus the center? All right, someone whose name is not Lily. Beautiful. All right. We made ourselves brave. We've listed 4 terms. General term. Thoughts? Beautiful. All right. We're doing plus ... at the end. All right. Let's do our quick interval of convergence for a geometric series. What should be true for our series to converge? The absolute value of x minus 3 should be less than 1. All right, now the question becomes, how do I figure out what inequality that means if I want to isolate x between 2 numbers? So where is the center? 3. What fancy name could I give this one right here? Nice, very fancy name. Radius of convergence. So remember, to make these 2 numbers, we could go 3 down 1 or 3 up 1. So what should my interval of convergence look like? Let's go 2, 3 minus 1, or 4, 3 plus 1.
Why is it?
Because this one, these were all centered at 0. So when I went either way, I had plus or minus the same number. Here, I was going plus or minus from a different number than 0. All right, I'm going to do the maybe a couple more of these and then ask you guys to do one. What I would like to say is sometimes these are a little bit easier to write, not necessarily in like this long notation, but they are kind of easy to write in Sigma notation. So I'm going to try that one in the next one, and then I'll have you guys try a couple on your own. Also, technically, you can center these anywhere you want. A lot of the time, it's easy to center them at 0, but you can get different power series depending on where you center them. So I'm going to try this one at 0, and then I'm going to have you guys try a couple in here. So just as a reminder, if we're centering at 0, we don't need to change this x, but I am going to put it on the back end of my fraction. So I'm going to do 2 plus x instead of x plus 2. All right, if I'm centering at 0, do I need to change anything about that x to make the center look right? No, I can just keep it x. If it were centered at 1, I would want to make an x minus 1. If it were centered at -1, I'd want to make it an x plus 1. What's next after changing the center? Make the 1. So how do I change a 2 into a 1? All right, I could subtract 1, but adding and subtracting is going to change the center. Divide by 2 or multiply by 1/2. All right, on the top, that makes us 2. On the bottom, that's 1 plus x over 2. Cool. So I'm trying to make this 2 into a 1, because in my sum formula, it looks like a over 1 minus r. So once I have this with my center that I desire, so here just 0, so that x is like x minus 0, I need to make this into a 1 to fit this sum formula. So I can pick out what A and what R are. Transitive property. Yeah, or no, commutative. You're right. Transitive is with something with equals sign. Oh, that's like if x equals 1 and 1 equals y, then x equals y. That's transitive. Yeah. All right. What's the last thing? So we changed the center. Didn't have to. We made it 1. What's the last thing we need to change? Make the minus. Anyone remember how we made the minus when we had a plus in the middle? Minus and negative. So we got 2 over 1 minus negative x over 2. Easily entertained today. All right. So what's A? 2. What's R? The negative x over 2. Now, I could write the first 4 terms and the general term, but sometimes on the AP test, you may just have the general term in your sigma notation. No, we would only need that if we're looking for interval of convergence. Here, they're just asking about the R itself, so we don't need absolute value. So if I wanted to write this in sigma notation, your geometric, to make sure that first term is the first term, you would want to start it at n equals 0, and you could just write A times R to the n, just like we've been doing for our general term every time. So if you want to do this, both on your problem set and here, instead of writing the first 4 terms in the general term, you could also just write it in sigma notation. If you find the power series this way, you'll always start at n equals 0. So I want to give you guys a couple of minutes to try these on your own, but with a little bit of instruction. This one is probably the more challenging of the two because you have to change the center. Be very, very careful once you change your center of how you change the denominator to make sure it's equal when you move on. You can try this one as well. Definitely a bit easier and a bit more. What? Yeah, exactly. And then for this last one right here, this is a manipulation from that guy to that guy. So we'll talk about that one in a second. So I want you to focus mostly on oh, goodness gracious, these 2 right here. I'm going to give you, what do you think? 6 minutes? 5. All right. Brandon's brave. Try 5 minutes for those 2. If you want to start with an easier one, I would start top right and then move bottom left. So you're changing the center, you're making the 1, you're making the minus. Is everyone excited for spring break? Like overwhelmingly excited. A lot of people absent today. All right, Sandra was both gone. Where's Kean? Kean gone. And then who's the other person here? Nick, thank you. Oh, and Sushan's gone again. Darn it. No, so theoretically, you could make it whatever center you want. I found it relatively easy to do 0, but it would also be super easy to do like a negative 1 if you want. This is the quietest you all have ever been. How unfortunate. All right, a bunch of people are doing really well with the first one, the 2 plus x on the bottom. So I'm going to write up a couple different ways to do that just so we can talk about it. That's not how 2 would look. Did everyone enjoy the tornado drill? Yeah, that kind of bothers me. I know. Yeah. Mm-hmm. Yeah, we actually had like a real tornado. It wasn't a drill. We did one a couple years ago.
Was it early in the morning?
Yeah. It was like the day before spring break too, I think. Because I was testing and I was like, we're not gonna be able to finish our test and we're going right into a break. Cool. Was that 6 years ago already? So old.
Oh, I was in my math class.
I was also in math class. All right, so let me show you a couple things. Wow, I just really distracted my whole class and then am mad about it. All right, so I'm guessing most of you did this question like this, yes? And you chose to center at 0. Just FYI, I could choose to center somewhere else. So where does it look like I'm centering here? -1. So if I don't tell you the center, you could theoretically do whatever you want. So just be prepared if you see something like this on the AP test, maybe the multiple choices. If you're having to write this yourself, maybe peek at the multiple choices and see what center they're playing around with. Yeah. What?
For the negative x squared.
Negative x squared.
You're like some that you have written.
Oh, because I dropped it. Thank you so much. Better? Was that what you were looking for? Thank you so much. Yeah, so both of these answers are perfectly accurate. Probably what the end result would be is that they would probably tell you a center, or based on your answer choices, if this were a multiple choice, you would be able to tell what the center is to kind of get a motivation going. What? Oh, I should have done that. Man, why am I being the worst today?
Wait, why is that one x plus 1 and not x minus 1?
Oh man, I screwed this one up. Let's fix it together. Wow. No, I'm tired. All right, let's figure this out. So 1/1, we need it to be minus. So x, let's see. I've got 2 plus x. So maybe like this instead. Is that equivalent? Nope, negative. Ugh. So it would still be centered here, right? Yeah, that works. So A would be 1, R would be negative x plus 1. So center's still -1. So I dropped my alternator. which is important. Better. All right, so let's talk about this one because this is more likely the one you're going to be able to see. Here we were centered at 2, so I'm going to create an x minus 2. What thing should I add or subtract to the bottom to kind of correct for what I just did? I like plus 4. With this minus 2 and this 2, I technically subtracted 4, so I'm adding 4 to kind of, because I subtracted 4 and added 4. So I'm trying to make the center of 2. So I'm trying to make x minus 2 in my thing. I can't just subtract 2 wherever I want. So I'm also adding 2, but since this was here. Yeah, it is like subtracting 4 and adding 4. Yeah. Exactly. 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 All right, let's clean this up. What things am I going to combine? Anyone know? The -1 and the 4, so that's 3. All right, so we made the center. Center's perfect. What now? I got to get the 1. So what should I be dividing everyone by? Multiply it by a third or divide everyone by 3. So we've got 1 over 1 plus, I guess I'll make it 2/3 x minus 2. Here, again, I really want to, whatchamacallit, preserve the x minus 2 part of that. And now, don't let me forget it. What did I forget last time? The negative. So I'm going to make this 1 over 1 minus -2/3 x minus 2. All right, writing this in sigma notation just because it's kind of easier. What's that going to look like? What's A? 1. What's R? Yeah, it's all that stuff. So I'm just going to leave off the A since it's 1. Multiplying by that won't do anything. -2/3 x minus 2 all to the n. All right. Last one I want to talk about before we kind of move on to the very last thing we're going to do with regular Taylor series. How does it look like I got from this one up here down to this one down here? Looks like I multiplied by x cubed, right? So I could take my whole series that I did. I'm going to take the one that was centered at 0 since we made that one a little bit cleaner and most of you guys chose to go that way. So I had n equals 0 to infinity of my 1/2 -x over 2 to the n. And I'm just going to multiply that general term by x cubed. We did that in our notes when we kind of distributed an x through the cosine one. Here, when we do this, we do want to make sure that we simplify this enough so that the x is kind of by itself to one singular power. So I'm going to take, let's see, I'm going to take this 1/2, leave him chilling there. Let's break off that negative. Would you guys agree that I could take that negative to the n power and make it like an alternator, like a -1 to the n? Yeah. All right. Let's see. I have x to some power. What power could I put on x if I want to put all the x's together? All right. Let's look. I've got x to the n and x cubed. What do I do to exponents? If I do like x squared times x cubed, I add them, right? So what should be the exponent? N plus 3, 3 plus n, either one's fine. I would argue I have a lot of 2's on the bottom. I got this 1, 2 from the 1/2 out front. I would argue I have more from the x over 2 to the n power. What power could I put on 2 in the bottom? N plus 1. From this 2 to the n and this singular 2. So fun ways we can deal with exponents. All right. I'm just going to comment on the next page. It gets a little aggressive. Yeah. Yep. So I'm coming from this 2 to the n and then this 2 to the first in the bottom. So 1, 2 from here and 2 from this side.
For the one on the left of it.
Yeah.
I'm good one.
2/3. So I took everything in this step and divided by 3 because I'm multiplying by 1/3 for everything.
Oh, I thought the 3 was.
Oh, no. We have to divide everyone by 3.
So this is.
All right. So I'm just going to comment on the next page. It has a lot of text on it. Really what we're talking about in this part is just if you have a given function and you end up taking a derivative of it or integrating it, and then they ask you to find the radius of convergence or the interval of convergence, all you need to know from this page, and we're going to kind of skip the bottom, is that the radius will stay the same no matter how many derivatives or integrals you take. The radius of convergence will stay the same. The interval of convergence can change. So what you would do in the case of that is you would just recheck your endpoints. We may see this on like a free response as we practice. I maybe bring this back on the 10.1 day and do this as an isolated question, but you guys know how to find interval of convergence already. So this is just like a very special case that we're not going to worry about. So for our ending of this part of Taylor series, I want to do one more kind of cute thing, and that's on the back page of this. So we're going to talk about finding sums using our elementary Taylor series. So I want you to look at the first one, and I want you to tell me, this looks like one of our Taylor series that we have memorized. Which 3 do we have memorized now? Sine, cosine, and e to the x. Which one does this look like?
Yes.
All right, I would argue, just like you guys, that this looks like e to the x. All right, because that's like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. What does it look like x equals? All right, we have a claim for 3. Does it look like I plugged in 3 here? I plugged in 3 here. 3 squared is 9. I plugged in 3 here and got 3 cubed is 27. So I would argue the sum of this is the e to the x at x equals 3. E cubed is my sum. So I now have a cool new way to find sums if I can recognize which Taylor series it is. Instead of plugging in infinitely many 3's, let's just plug it into the other side that I know it's equivalent to. All right. What does the next one look like? What does this guy look like? He has powers. Let's see. We have 3, 5, 7 factorial in the bottom. I would argue this looks like sine of x. That one went x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. What x value does it look like they plugged in? 2. So that's x. That's x cubed. 2 cubed is 8. Is 2 to the 5th 32? It's 2 to the 7th 128. Sure. All right. So what is this all equal to? Cute. I think so. That's just the answer. So we just have to recognize the Taylor series. Everything looks so easy. So I think this unit is not actually terrible. It just looks terrifying. If you're willing to write and take things step by step, it's really not too bad. Would love to. All right, this last one. What type of series does this look like? Does it look like cosine? I don't see any factorials in there.
Geometric.
I think it looks geometric. Doesn't it? Wait, what do I need to know to find the sum of a geometric? We talked about it. Don't we need to know A and R? What's A? First term. What's R? All right. So what's my sum? How do I find it?
First term over 1.
And simplifying, should we do it? Okay. Cool. This would be a fantastic multiple choice question. You would only have to simplify it if the multiple choice question made you. So you do. I would love to. How many thirds are in one? 3 plus 2 is 5/3. Well, if I do 1 divided by 5/3, 3/5. All right. Just take your time on it. We recognize this year we might have to spend more time on fractions than we normally do. That's okay. And we'll practice that as we work towards our free responses. All right. So what my plan for the rest of class is, I have an answer key to the problem set. I would love if you worked your way towards also having answers to the problem set. So can we, all of us, if you get the questions right, absolutely. What I'm going to walk around with is my answer key and some stickers. So if you can show me a correct answer, I will reward you with a sticker. I am going to try to find some fun ones. I had glittery stars in my AV class. We currently have, look at my face, 12:24. When do we get out of here? 1:05. We have 40 minutes to work on our problem set. If you are not working on your problem set, every single one of you, guess who gets to do this example that I skipped? You guys. So please work on this problem set. You're working towards getting those bonus points by turning it in on round 1 day. You cannot do 13 and 14, and that is it. You can do every single other question. Yeah. So if you see anything about error bound, you don't want to do that. Oh, okay. Oh, I should tell that's Why is there so much? I thought there'd be like 2 days for anyway. Oh, he's trying to forget these. Yeah. First one. Okay. All right, Austin, help me figure out some free stickers. How you do first? The whole one?
Yeah. Oh, I don't think
No, I guess no one gets. Oh no, we got sticker choices. All right. We got sparkly stars. We got smiley faces. We got other ones.
This is what number
Hold on.
it is.
Where did my the numbers on that one get really gross? Oh, yes. If anyone's working on number 4, the numbers are super gross. Just it's okay. I promise. Whoa. I'm kidding. Yeah. Can you either or me write the summation notation or yeah, I'm oh goodness. Does anyone ever use 0.5 lead and it just breaks all the time? I'm kidding.
I
don't believe.
like to see I get wrong, so I don't make the same mistake each time. No, I don't. But right, and there's I do it.
I should have just said no.
Should I stop the recording? We're not really doing anything right now. Bye, recording.